All right. Good morning, everyone. Welcome to day 2 of the Columbia Crypto Economics Workshop. Very cool program today. A lot of great talks, a spicy panel to wrap up everything at the end of the day. You can find the agenda at this QR code here. Couple quick announcements before we get started. I'll just mostly let you read this, but so like yesterday, no food and drink up here, so all of the receptions, which we'll have, and the breaks that we'll have and lunch, that'll all be downstairs near where you walked in. Restrooms are either sort of around the corner or downstairs. And let's go ahead and kick things off with session 5 on block co-creation. Julian will be the chair.
Good morning, everyone. Welcome to the block co-creation session. We'll have 3 presentations today. One will be by Malesh Pai on the economics of censorship resistance and multiple concurrent block producers. One will be by Thomas Thierry from the Ethereum Foundation on the Brave New World Computer. And after that, we'll close off with a discussion hosted by Pranav. So without further ado, I'd like to welcome Malesh Pai from Rice University and Consensus for Economics of Censorship Resistance and MCP.
All right. Wait, no, that's not right. There we go. All right. OK, so thank you to the organizers for including this, and thanks to all of you for showing up at 9 a.m. I'm going to talk about multiple concurrent proposers, why, and this is one of the dangers of letting economists near consensus. A, you get these kind of talks, and B, you end up with a discussant. So I want to stress that this is still early stage work. This is work in progress. It's been influenced by collaborations with a whole bunch of people. And it's nowhere close to it's not like an EIP I want to ship next week. This talk is just, it's sort of also not a standard talk for me. I'm an academic. This is like a progress report, basically. Tell you where we are, tell you why we think this is important as an end game, and tell you about the roadblocks to getting there, OK? All right, so what's the story? Things that all of you know in this room. Most blockchains in production are leader-driven. That means a single leader is in charge of deciding what goes to the next block and in what order. How you select that leader depends on the particular blockchain, but that's almost always the way things go. And this whole thing about MEV that we've been sort of wringing our hands about for the last 5 years stem from that monopoly power that we've handed the leader. So there might be millions or thousands of validators. There might be thousands of proposers. So there's a lot of competition in the system. But if you want to get into the next block, this leader is your only hope, OK? And the problem was actually observed, I don't know, a decade ago. So this is a blog post by Vitalik back in 2015. And he makes the following simple point, which is consider a really simple European call option that we're contracting on chain. So I'm going to pay you the difference between, let's say, the price of ETH and USDC. I'm going to pay you any amount that it goes above some strike price P at a given block X. This is a very funky option. To exercise this option, you have to get a transaction into that block X. So of course, at block X, suppose the option is profitable. Let's say the price has gone up to 10 above the strike price. That means that you, the person who's got this option, are willing to pay up to $10 to convince the leader, hey, include my transaction in the block, please. But of course, the person who would be stuck paying you out if that transaction gets into the blockchain, I'll be out $10. So I'm willing to tell the leader, hey, here's $10. Please make your transaction go away, OK? And in a frictionless market, the price of inclusion must be $10. And sort of the thought experiment, the question, the existential question that Vitalik had was, if the gains from transacting accrue to a proposer, why contract this option on-chain in the first place? Why should we do smart contracting? This is not this is not specific to that example per se. This is something that is at the heart of anything when multiple people are contending for a piece of state. So a lot of the valuable applications, I'd argue like most of them, involve, with the possible exception of like payments, like a lot of stuff that we care about involves resolving state contention. So who gets to take a given bid or ask is sort of, you have to decide who gets to take it. And in traditional finance, that competition is resolved using a trusted intermediary and a known advertised in advance rule. For example, the New York Stock Exchange uses time priority followed by price priority on the continuous limit order book. In the traditional blockchain, like I said earlier, the proposer has a temporary monopoly over the state determination, which means that any profitable opportunity with contention is going to leak this excess value to the proposer. Some people have said, OK, let's just make the chain go faster. Let's get more space in. More space is great. Faster chains are great. They will reduce the average fee that a given consumer who wants to transact on the chain will have to pay. But if there's state contention, then the bottleneck is still that the proposer decides, and the proposer will have to be paid off. So without something else, whatever that something else might be, liquidity providers are still going to lose money. DeFi is still going to be long-term unsustainable because the value of transacting is moving from the people who are doing the transaction on this supposedly credible neutral block space onto the proposer or the person in charge of announcing the block. So, I'm now moving from academia to crypto, so I need to put a meme in there somewhere. So what do we want? Okay, what we want, per se, is this happy space where all valid transactions get a fair shot at influencing the state transition that they want. And I'm going to put fair in quotes because I don't really have a definition of what I mean by fair just yet. And what they want to do is they want to be able to do this for contracting on chain to be profitable. You need to do this without leaking too much value to the proposer. That is to say that the proposer should get paid proportional to the value of the block space, not the specific state transition that is being implemented. The value of the state transition should be distributed among the parties that are the counterparties in that particular state transition. What we've got is something else, which is when there's contention, and then the competition is going off in terms of tips. This could be like priority gas auctions, which we had before. It could be MEV Boost, which we've got now. It could be in other versions of MEV Boost or versions of PGA, like you've got Jito and all that in Solana land. Like you've got some version of that. And the thing that you need to notice is that these payments can be arbitrarily large. So this is not just a theoretical concern. Like on August 5th or August 6th, when the Bank of Japan governor suddenly raised rates and no one was expecting it, the next 5 blocks went for 300 ETH each. Okay, so this is a large amount of money that is leaking out of the system and into payments to the proposer. So what's our take on this? Our take on this is that the MEV problem isn't necessarily one of ordering. It's you can always execute the blockchain. You can always execute the block that you have in a different order from the one you have. It's that the set of valid transactions that are trying to influence the state don't necessarily make it onto the chain. It's censorship, in other words. Vitalik recognized this in 2015, but the implications are, I think, a little worse than he recognized. And in an earlier paper, we pointed out that without a specific notion of censorship resistance, so I'll try and be a little more formal about that in a second. Without a specific notion of censorship resistance, you can't run an auction on chain, at least over a single block or over a few blocks. And more generally, the set of mechanisms you can run or how much value you have to account as accruing to the mechanism versus how much is leaked to the proposer are determined in equilibrium by this notion of censorship resistance. So critically, what I mean is the term censorship resistance has gotten a little overloaded, and I think that's where some of the confusion is stinging from. Just the fact that the transaction is on-chain does not necessarily mean that it's censorship resistant, because the proposer might have chosen to put it in a way that it can't influence the state transition that it wants. That's still censorship. That's just not the one we're talking about. So what's our definition of censorship resistance? It's a very simple one. We're going to abstract away from the machinations of a blockchain, and we're going to think about a public bulletin board that has two functions. It has a write function, which takes a message and a tip, and sort of either succeeds or fails. The tip is the amount that will be paid to the proposer if the transaction gets included, if it doesn't. If the message gets written, sorry. And the read is just something you can always read the bulletin board. What is an economic definition of censorship resistance? An economic definition of censorship resistance is a mapping that takes as input the tip in the write operation and outputs the minimum cost that a motivated adversary would have to pay to make the write fail. So I'm sort of just saying that if you can get stuff on a bulletin board, you can do stuff with it, but then people might have an incentive to keep it off the bulletin board. How much would they have to pay? In a simple single block setting, for example, if your bulletin board is what's in this block, then like the call option example, it's just the cost of that. It's just the tip. You can pay T to get in. Somebody else can pay T to keep it out. What we showed in that paper was that suppose you extended the notion. So instead of your bulletin board being one person, there were multiple people who could all write to the bulletin board. And you allowed what we call conditional tipping. So what is conditional tipping? Conditional tipping is you have two numbers, a small tip little t, a big tip capital T, and you say, I will tip little t if multiple people write my transaction to the bulletin board, but I will pay capital T if only one person includes it. Then we basically showed that what you get with this conditional tipping construction is really good censorship resistance in this economic sense. Why? Because to get on chain, you pay at most k times little t, but the cost to censor is k times capital T. You'd have to pay each proposer the big tip to keep them out, to keep the transaction out, but if any one of them succeeds, in writing to the bulletin board, the transaction is there, and people can then decide how to influence the state transition. So with the main idea is, when I first got into crypto, I was trying to understand why everyone kept writing 33 and hat and whatever in their crypto handles, and I was told, oh, wait, it's the prisoner's dilemma. Well, this is the prisoner's dilemma all over again. We're basically setting up a prisoner's dilemma among these multiple concurrent proposers by having conditional tips. It's expensive to censor any given transaction, but it's cheap to include. Okay? So now comes the part where you start, where you need to actually make this thing work. So intuitively, if we can pay, and there's still a big if, or there's some amount of if, and I'll tell you where we're stuck or where we've gotten to. If we can pay the consensus complexity of having multiple concurrent proposers, we automatically solve MEV since no single proposer has monopoly power over inclusion. So the monopoly rents that you had are gone. The main sort of, well, what do you need to do this? Well, you need two ingredients, multiple proposers, because you need multiple of them for the reasons that I said, but it has to be like the public bulletin board. As long as any one of them succeeds getting it onto the bulletin board, it has to succeed. In a state transition sort of framework, that means that no single one of them gets a veto on any state transition. And without this property, the fact that any one of them writing it to that bulletin board means that that transaction can influence the state transition. If one person has the veto power back, then that person is the monopolist for the purposes of that state transition, and it's going to extract the monopoly rents. And the other part, which is what I'm going to spend most of my time talking about today, is the concurrency. So multiple concurrent proposals, you can break it into multiple and concurrent. Well, concurrency is important because without this, you get a last look problem. One person gets to see more about the state of the world, and that can be useful. So how are we going to do this? Well, this is sort of a sketch. We think a really simple construction can work. You have basically multiple subchains. So any given slot, you have multiple people who are proposers in that slot. Each of them announces a block. The set of transactions that you're considering as the valid block, as the block in that slot, is the union of the blocks that have been announced by each of these multiple proposers. All right? So it's take your favorite consensus, algorithm, take the validator set. Instead of having one proposer in a slot, have k proposers in that slot, and essentially have the same validator set run k separate chains. This is just a linear scale-up. Execution will have to change. But if you can do one blockchain with n validators, you can do k blockchains with the same n validators. That's not the hard part. The hard part is reasoning about the incentives from there. So after the consensus on the union, the execution or state transition has to be done. It's going to be done according to some agreed upon deterministic rule. The one that's probably easiest is, and nicest is the decreasing order of priority fees, the priority fee mechanism of Dan Robinson and Dave White, somewhere here. But you could do other things. So application-controlled execution has been all the rage lately. I'm not going to use the other acronym that's going around. And potentially others. So that's sort of our high-level construction. What are the consensus properties? Well, let me just shove that under the rug, because you don't want to hear me talk about consensus. But we believe this could work, and we'll have a paper soon. Yeah, OK. For today's talk, I want to give you some reasons why existing censorship resistance gadgets, existing like Fossil, which Thomas is going to give you a fuller description of shortly, why they aren't sufficient for our desiderata. I want to be clear, they don't claim to be sufficient for the desiderata. I just want to explain where I think the gap is, and why a full MCP construction might be enough. Hopefully the censorship resistance story, the conditional tipping story I told you tells you some of that, but what else we'll need to make it work, okay? So sorry for, and this is, Thomas is going to tell me what I got wrong, but here's my understanding of Fossil, fork choice, and forced inclusion lists. And it's a very elegant idea. It's basically, instead, in constructing the block, before the proposer moves, a committee of validators each proposes an inclusion list, which is some set of valid transactions that they see. The proposer must include, and there's variants in terms of how much these inclusion lists constrain the proposer, but basically the idea is that the proposer is constrained to include at least some subset of these transactions, and if you don't include enough of these transactions in your block as the proposer, then the block is not valid, okay? What does this do? This solves a different related notion of censorship resistance, which is indeed important for a neutral block space. But for example, suppose there's a whole bunch of proposers who are censoring Tornado Cash transactions. Not anymore, hopefully, but that was the thing. As long as the inclusion lists include these as long as the committee inclusion lists include these transactions, then given the constraints on the proposers are obliged to include them. So the main thing it's doing, as I understand it, is that unlike the regular mempool, where you can just say, oops, I didn't see that transaction in time, here, proposers don't have plausible deniability. It's part of the fork choice rule of the blockchain. You've gotten these inclusion lists. You can't say, oops, I didn't see it. All right? What does it not do? To my understanding, it does not solve the problem of censorship resistance in terms of the definition that we laid out. So for example, if there is a short-term arbitrage opportunity, the proposer is the one who's determining the ordering of the block, and therefore who gets to take that arbitrage. If you plan on changing the ordering rule, you have to reason about everyone's incentives, including the proposers and the inclusion list. And there are variants that are trying to start reasoning about inclusion list proposers as incentives as well. But I'm going to not talk about that. The other point I want to make is that by designation, there is a set of early movers, the inclusion listers, and a last mover, which is the proposer who actually announces stuff. Since the proposer moves after the committee, they have more information about the state of the world. For example, time has gone on, another few seconds have gone by, and prices on Binance have changed. Time-sensitive transactions, therefore, we believe will not use the inclusion list route to get on chain. They will still have to go, for them, this is still effectively a single proposer chain, and the numbers sort of suggest that about a third of MEV-boost payments are estimated to originate from SexDexR. But to be clear, this is like a wide confidence interval that goes from 10% to 75%. So 1/3 is, I pulled it out of a hat. So last look advantages. Let's try and model and understand seriously what we mean by these last look advantages. So think of just two bidders, Alice and Bob, in an auction with a reserve price of 0. So think of it as there's an arbitrage opportunity. Alice and Bob are the two people who can claim this arbitrage opportunity. The value of the arbitrage opportunity is the value of the arbitrage opportunity. The trouble is they're going to move at different times. So Alice is going to bid at time 0 for this auction object, and then the object's value is going to evolve. Bob's going to bid at some time t later than Alice, and in particular, Bob is going to have superior information, so Bob is actually going to see the value of the arbitrage opportunity. Alice at time 0 is only going to know the distribution of the value of the arbitrage opportunity, like what she expects it's going to be worth, knowing that Bob is going to be moving after her, and at that point is when the value of the arbitrage is realized. In these settings, we have something called the winner's curse. So what is the winner's curse? The winner's curse is basically Bob gets to sit back and snipe the object. And there was a lovely talk by Julian, actually, at SBC last year, MEV Day SBC last year, where he also made this point, which is Bob gets to see this thing here, for example, is when Alice decided to move. This is the price Alice saw. If the price of the object has gone up from the time Alice decided to move, Bob can say, OK, it's worth more to me. Let me pick it up. If Alice has decided to, if the price has gone down, Bob can say, Alice, I don't want it. You can have it. So why is this relevant? Imagine like Alice is an arbitrageur trying to get inclusion via an inclusion list. Bob goes straight to the main proposer. Then this sort of thing says that Alice can't make any profits this way because Bob is always going to pick her off when her sort of bid was profitable. And conversely, Alice is going to end up with the good exactly when her bid is unprofitable. Now you might say, aha, that's because you're saying Bob can exactly see Alice's bid, and Bob can decide to penny snipe her or not. So what if Alice or the inclusion list uses some form of privacy encryptions, whatever you want, so that we can't, so that Bob, when Bob is submitting his transaction, doesn't know what's happening? Well, with Dan and Siamak, we started down the process of solving this model. So here's so now imagine Alice moves first, Bob moves later, but at the time Bob bids, Bob knows the value of the object, so he has superior information. What he doesn't see is he doesn't see Alice's value. In that case, you can show that the equilibrium is an intriguing one, which is that Alice is going to behave as if, even though she doesn't know the value, she knows it's going to be drawn according to the distribution. She's going to just randomly draw a value from the known distribution and bid as if she's bidding at Bob at the time Bob is with that value. So in particular, she's going to draw a value from the distribution and bid the conditional expectation conditioned on the realized value being smaller than her drawn value, V prime. Bob is actually going to see the value of the object and bid the conditional expectation conditioned on the realized value being less than V. Now, of course, this means that sometimes, because Bob is bidding less than his value, and Bob doesn't know Alice's bid, this means that unlike the previous case where you had exact perfect unraveling, you're not going to get exact perfect unraveling. Alice is still going to win the good sometimes. It's just that in expectation, this equilibrium is going to be unprofitable for her. So she is still going to make an expected payoff of 0 in this auction. And cute aside, Bob's payoff is going to equal the value of an exchange option. So what is an exchange option? It's the right to exchange an asset for a different asset, which is IID. So Bob is going to make money in this auction. Alice is not. Okay? That means that, of course, this is presented as a criticism, or not a criticism, but like this is why fossil can't work for these kind of time-sensitive bids. Of course, this also means that we need to be able to enforce the concurrency in multiple concurrent proposers. We've already seen timing games in single proposer settings where the proposer waits a little longer than their scheduled block time to try and have more information. It's actually, in the single proposer case, it's just to let the auction run longer and get more bids. You also steal some bids, steal some transactions from the next person's slot in theory and so on. But with multiple concurrent proposers, if they're not perfectly concurrent, you've got yet another reason for timing games, which is the last look advantage. In progress, are timing games worse under multiple concurrent proposers than with a single proposer? We'll wait that up. But what that means is we need to actually formally define concurrency, and we need to define what are the desiderata that what do we mean by concurrency. So here are two definitions, potentially, of concurrency. One is a weak definition. So the weak definition just says that each proposer doesn't get to see the other people's proposals before they propose themselves. In the language of game theory, that means that your information set is, you might know more about the world, but the one thing you cannot do is condition your strategy, the block you propose, on the block other people's propose. Weak simultaneous release will avoid the first kind of last look problem, the kind of perfect unraveling that we talked about. But weak simultaneous release, even if you don't know the content of the other people's blocks, you might know more about the state of the world. And to fix that, you need strong simultaneous release, which includes, sort of parameterized strong simultaneous release, which means you want to include that, but you want to include the weak simultaneous release property, but you also want that any given proposer doesn't know much about the additional stuff about the state of the world. So you don't get to, even if you don't know the other person's proposals, you don't get to sit and stare at Binance for a second longer. And this is a harder one to fix. We think the first one can be straightforwardly taken care of at the cost of maybe an extra round of communication by some form of commit reveal. Right? So proposers, instead of announcing a block, they commit to a hash. You form consensus on the hash and tell the others you're out. And then when everyone's got consensus on the hash, you then reveal the contents after the consensus on the commitments. There's an issue, of course, you'd have to slash people who then choose to turn around and not reveal their blocks, so you have some kind of bounded incentives. You could use fancier encryption. So for example, you could have blocks that are time lock encrypted, and in the happy path, everyone reveals, but if they don't, they can't just get, it's not just that they get slashed, but we don't know what their block contents are, we can actually force their block open. And you know, if you talk to enough cryptographers, they always have brilliant ideas on how to enforce these things. The harder one is indeed enforcing strong simultaneity. So you need incentives to actually measure each other's wall clock time, and we're working on that. Like I said, this is a progress report, so there's a bunch of other upsides and downsides. I've only sketched to you what might be possible if you get 2 multiple concurrent proposers, but you need, of course, we need to fully flesh out an implementation. We believe we'll have one soon. So you need to think carefully about the communication complexity and sort of the forking paths problem of like different people, like there are now k proposers, so potentially like 2 to the k different forks. The number of forks could be exponential, so need to think through that. And of course, having it in this place means that you're changing the execution client, you're getting delayed execution. You need to rethink through how you're going to do transaction fee mechanism design. You need to rethink through how block building might happen. I should be transparent that just because you're adding multiple proposers doesn't mean you're getting a linear throughput increase, because the same transaction might get added by multiple proposers. And the biggest worry, of course, is that if all these concurrent proposers collude, then you're effectively back to a single laddered chain, but just with a lot more consensus overhead. The but on this is that you can work through the game theory, and the incentives to deviate in any given block will be strong. Any given block proposer, if everyone else is proposing a block, you can basically get a potentially much higher payoff by sort of deviating from that and announcing your own block. So because they have like the k-1 people have to split up the rents of the block across themselves. You can be just the one guy offering better inclusion on your side. When we get to the other side, hopefully I've convinced you that this greatly simplifies the Scourge section of the Ethereum roadmap, in the sense that you will basically, when you get to that side, if you work through these problems, you will get -5. You will get You will get censorship resistance, and then once you have censorship resistance, you can have a lot fancier and nicer mechanisms. The owner of and the other upside to us is that the owner of a piece of state controls the rent to access that state and removes the need for off-chain devices and so on. So I'll stop here. I'll take questions if needed, and otherwise I'm around. I mean, look, we know how much the MEV boot. Oh, sorry. The question was how much do I think is being lost to dApps from the current leader-based monopoly system? We know sort of a lower bound to the answer to this. We know that the lower bound is sort of how much builders are paying for the right to buy the blocks on MEV Boost. And we know that that number is of the order of like 1 billion, 700 million or so a year, okay? Now, the thing I want you to think about is what is the total value generated on the, so this is for Ethereum, by the way. What is the total value of finance transacting on the Ethereum blockchain? Because 700 million, do you really think 70 billion of economic value has been generated? If 700 million is like 1% of 70 billion, So unless you think you've generated 70 billion of value, you've got a system like that is basically as bad as credit cards. Okay? So that's why I think it's a large magnitude. And the other thing is just, without censorship resistance, you limit the set of mechanisms that you can run. So this opens up the design space for dApp developers. A lot of the questions about like application-controlled execution come from the fact that dApp developers want control to the access to their state rents. And getting that back on chain rather than needing them to resort to off-chain gadgets might be a good thing. But I'm taking up time. I apologize. Thank you very much.
Thank you, Kiran. Up next, we have Thomas Thierry from the Ethereum Foundation speaking on A Brave New World Computer.
Can everyone hear me? Is it coming from here or from here? Okay. Yeah, so I hope I'll have time to later to refute some of the arguments Malesh made and make it a bit more spicy. But I wanted to just talk about a bit of a higher level of like what I think or some of us think could be the future of censorship resistance for Ethereum, or newly rebranded as the World Computer again. And I will start at a quite high level. So the Ethereum protocol very broadly can just be thought of as like a set of specifications. And these specifications will define the rules, the roles, the duties of like a set of participants, and that are like tasked with maintaining and updating a distributed ledger. And that distributed ledger happens to be structured as a chain of blocks, and each block is filled with user transactions. So when you say it like this, it's a bit dull and boring. It's like, oh, okay. But what's very exciting, at least to me, is like the properties this ledger or the chain has. And these are censorship resistance, permissionlessness, transparency, immutability. And I think those are like kind of the unique properties that make blockchains very cool. But for these, I guess like 2 points, those properties are like very, very crucial if we want Ethereum and blockchains like Ethereum, let's say, to be the world computer and like the, I don't know, the neutral infrastructure on which like everyone can build on, and like the internet of value. I think those are like very crucial. And to get some of these very crucial properties like censorship resistance and permissionlessness, you need to rely on an actually decentralized set of validators, of participants, let's say. And so, yeah, on Ethereum, like I was mentioning, like it's a set of specifications, but like the specifications are actually telling an actual network of computers that are called validators on Ethereum to do tasks and fulfill duties. And you have, yeah, you can broadly separate these tasks into two. You have consensus on the one hand, and it's just like the process by which just validators will agree on the state of the chain. And then you have execution, and execution is like the actual processing and validating of transactions via the EVM. And if you notice, on Ethereum at least, validators are actually doing both tasks, at least originally, and it's kind of like important to keep that in mind for the rest of the talk. And they are also both doing proposing sometimes when they are elected to be a proposer and like broadcast the rest, the block to the rest of the network, and attesting, which means validating blocks when they see one. Okay, so I said like those crucial properties were like very important and relying on like an actual decentralized set of validators. So maybe we can look at how we are doing today. And this is the data that was done by Chainbound last year in the context of an ROP. and it looks at the actual like geographic distribution of validators, not nodes, across the world. And I would say we are doing pretty good. Like, of course, like we have some more progress to do, for example, in some continents like Africa. But like generally, like the set of validators is actually quite distributed. We have around 10,000 nodes and 1 million plus validators. And when you look at the stake distribution, it's doing pretty good as well, I'd say. You do have like big entities like Coinbase and Lido that are like controlling large parts of the stake. But I mean, even Lido can be broken down into like many node operators. So no, I think it's, well, at least my opinion is it's looking pretty good. But, and there is quite a big but here, remember that validators were also in charge of execution duties. And it's a duty, but it actually comes with like a lot of power. Because it means you have the power to build blocks and like order transactions in the block. And this ordering of transactions generates value. That value is called MEV. We've talked a bunch about this, I mean, today and in the other talks. And yeah, the catch is like to extract that value efficiently, you need to be sophisticated. And that is in itself a very big centralizing force. So the idea was to say, okay, we want to shield proposers and validators from this centralizing force. So we'll just like outsource this like sophisticated task to builders that are like sophisticated and centralized entities, but we don't care because basically they will build the blocks, they will be sophisticated, and then all the validators will have to do is just like pick the blocks with the highest value without like becoming centralized. And so that's all good. But then we introduced a new class of actors now, and they have like power over like the block content of on Ethereum. So we also need to look at their distribution, I guess. And it doesn't look so good anymore. It's okay. This is a bit exaggerated, I guess, because like, I mean, you have more than 2 builders, but in effect, like they actually like make about 90% of the share of like the market share of the block market. So you have 2 builders, Beaver and Titan. And now this is a big problem for some of the properties we want to have, right? Because now it means like for censorship resistance and permissionlessness, basically if those 2 entities like don't want to include your transactions, you will have to wait like a while before it gets included. And so, yeah, we need to do something about this because otherwise we lose some of the like core properties that make blockchains as cool as they are. Yeah, there was an example, very, very striking one, directionally good, but like still striking, like a couple of months ago. One of the major builders just like stopped censoring. And we can see like this huge drop in censorship in the network. And like, yes, directionally it's pretty good, but like you can see how fragile the whole like censorship resistance of Ethereum is right now. And so that's something we want to improve. And yeah, what can we do? Well, inclusion lists. And I think it's a very neat and simple idea, but like the very core simple idea is to say, okay, now we have like this set of decentralized validators, and we have this very centralized set of builders. So the idea is to say, okay, the proposers will define a set of transactions that need to be included by the sophisticated builders for the block to be valid. Otherwise, it just can't be valid. And so what this does is like it gives back some power to the validator set, which is decentralized, to constrain like the builders that are actually centralized. So that's the core idea. And there was like a ton of work done on inclusion lists. There was even an EIP, 7547, that was considered for inclusion, but then rejected for like some compatibility issues and some technical details. But at the same time, there was also like all these like different research threads. So you had, multiple block co-construction that was like coming with like things like multiplicity. There was also like some more research on like the view merge stuff for fork choice. So it was like a bunch of research in a lot of different areas. And what Fossil is basically we took inspiration from all these research threads, and we came up with like a very, very simple mechanism that allows multiple validators to construct inclusion lists together. And those lists will constrain the block builders and make it very hard for them to exclude transactions because otherwise their block won't be valid. Okay, so how does it actually work? You have 16, each slot, you have 16 validators that are randomly selected, and those will be the IL committee members. And what they will do is like just monitor the mempool, the public mempool, take transactions, put them in their ILs, so inclusion lists, and broadcast them to the rest of the network. And then the rest of validators will just like monitor these ILs and see them and store them as they come until 9 seconds into the slot, and that's the view freeze deadline. So they will do this, and then after the view freeze deadline, the validators can still like forward lists, but like they don't store new ones. The second step is very simple to understand. The builder will just like monitor these ILs, and then he actually has like more time than other validators to construct to monitor and store these ILs, and this just ensures like he has enough time compared to the other validators to actually make sure he sees like all the available inclusion lists. It's a detail. And what it does is just like, it takes all the transactions across all ILs, and he has to include them in its block. So quite simple. And then what the attesters do is they do exactly the same thing as the builder, but with the inclusion list stored until the view freeze deadline. And they just make sure like all the transactions that are seen according to their view are actually in the builder's blocks. If there are, like everything is good and they just vote for the block. If some of them are missing and should have been included, then they don't vote for it, and that block will never become canonical. So that's Fossil. And it relies on a few very core properties that I think make it very cool. One property is like the same slot property. So yeah, the payload and the IL transaction, the ILs, can actually be constructed at the same time, like during the same slot, and just need to be merged at the end. So you get like some real-time censorship resistance properties, which is very nice. The second one is, we have multiple IL committee members. So what's really cool is like, okay, first it gives like some robustness against like commitment attacks, like bribing and extortion attacks, because you have to, for example, bribe all the committees for them not to include a transaction in their lists. But it also gives us this 1 out of n honesty assumption. So you need only one IL committee member to do its job honestly and not censor for the mechanism to completely work. And then, two other properties that are like quite related to what Malesh was saying. The first is the conditional property. So the builder only needs to include transactions in its block until that block is full, so until the gas limit. Otherwise, he can exclude some. And then he can include IL transactions anywhere in the block, and those are not ordered. And so, a very, very important thing to understand is like Fossil. Okay, so we can debate definitions, I guess, on what censorship resistance is, but Fossil is not trying to solve MEV. And that's, I think, like things like MCP and Braid are like trying to do both things at the same time. They're like trying to solve MEV and solve censorship resistance. Fossil solves censorship resistance, but is not trying to like interfere with like the current market structure of MEV. And so these two properties actually make it very robust against MEV transactions crowding the ILs. So what you don't want basically is like, we have this cool gadget and it's censorship resistant, but then like imagine it was like with dedicated block space that needed to be at the top of block, like 100% we will have like an IL boost and people will try to like put their like very valuable transactions in the ILs, and then the whole thing is defeated because now you don't have like a censorship resistant mechanism, you just have like additional block space for everyone to take advantage of, which is a bit ridiculous. So I think letting the proposer or the builder or the block producer generally just like kind of still being able to be in control of what he wants to do and explicitly give him the last look is actually a good thing for censorship resistance. Otherwise, you don't, like, you get the idea. But yeah, so a nice, cool way to see Fossil, I think, is to also see it as the solo staker signal boost. I like this idea because, okay, imagine, assuming we have like around 6% solo stakers today, now, like, if the builders want to censor your transaction, you actually, and okay, solo stakers, let's say they are independent and they build their own blocks and they don't censor. Okay, those are assumptions. If the builders are censoring your transaction today, you actually have to wait on average for 17 blocks until your transaction will make it in, which is crazy. Like, it degrades the UX so much that you can basically make it terrible for anyone that you want to exclude to use the chain. With Fossil, you actually have a 64% chance of having at least one solo staker in your committee, if you have 16 committee members. So you now just like need to wait like 1.6 blocks on average until your transactions will actually make it in the block, which is like a huge difference. And it's only with 16 committee members, and yeah, I think it's just like a nice way to see it. Another cool way to see it, I think, is like to see as Fossil as building like the raw template blocks that needs to be included, and then having the proposer like kind of refine this block and kind of make it more fancy, I guess. But like you can also see Fossil as like a way to give power to the decentralized validator set to really build the core template block, and then allow like a sophisticated entity to just like refine it. I like to think about it this way. Yeah. And then a claim is to, if we want to claim that the world computer we are building is actually permissionless and censorship resistant, then like I think it's a really good idea to like give power back to the validator set, which is decentralized, but also to boost the signal of the actual validators that are providing these properties in the first place. And I think these are solo stakers. Okay. Yeah, okay, so I think what's really cool about Fossil, another thing that's really cool about Fossil, is that it's very suited to extensions, and that's what I'm most interested in right now. So now, it's an EIP, so it's like a candidate for inclusion in like an upgrade, but it can be extended into like very different directions. A very obvious one is blobs. We just want like to extend the scope of Fossil so it can include blob transactions. That feels very obvious. Another one is incentives, how to reward IL committee members. Because right now, in the current version, we are relying on altruistic behavior, which I think is okay because like we have this 1 out of n honesty assumption, so it makes it fine, but like we can probably do better. I'll touch on it a bit later. Oops. I think it's very important also to think about anonymity and privacy. Like it would be very nice if the ones that are, like the participants that are contributing to the censorship resistance of the network didn't have to be linked to a specific set of transactions they want to include. They could be protected against like retaliation and like, I don't know, it will just be very nice, I think. And then the MEV part that Malesh talked about is like, yes, do we want to like avoid the last look and have these kind of properties, but all these things, to me, have to do with MEV, and we have to be very careful about not centralizing the validator set either, because like we have to understand that people will probably try to play some games at any point. And with MCP and Braid, like we give a lot of power. Like we might expect a lot more centralization from these validators if we go towards a world where you have multiple concurrent proposals that are sophisticated. One very promising avenue, I think, is if we have APS, so if we successfully shield the validator, attester set, and consensus duties from sophisticated execution proposals, then having MCP for execution proposals is actually a good idea. Because now they can't really hurt consensus, and they can play timing games, and we don't really care. And yeah, the last kind of thing I wanted to make a case for is maybe thinking about includer separation, so maybe just like calling them includers in the first place instead of IAL committee members, which is a bit long. But yeah, imagine a post-fossil, post-APS world. So we have successfully shielded the consensus duties from sophistication and timing games and everything. And you have like these very sophisticated, high capital requirements execution proposals. And then on the other hand, you have attesters, the beacon proposer that is just like making the consensus block, which is not sophisticated, and includers. I think that's fine. That would be great in the first place. But I think there is a case to be made for includers that are separated from attesters, because they have extremely different properties. Like attesters are like actually very crucial for the economic security of the chain. So they need to be staked like with at least a decent amount of stake. We have exit and deposit queues because they can't like go in and out like so quickly for consensus reasons as well. Whereas includers, like I think there is a case to have them just like have like very good UX that allows them to come in and out of the protocol like very quickly, include like transactions, participate in the censorship resistance gadget without like being like very like having a lot of stake at all. And if we want to do this, I think there is also a case for an independent reward mechanism for them. So that might be inclusion fees. I think Dan talked about inclusion fees in his first presentation. I think there is a case for like an inclusion fee that allows like includers to come in and out of the network based on like the levels or state of censorship on the network. So I think that's a promising avenue as well. And yeah, I talked about this, but like anonymous ILs, we have actually some work on this. And you can combine linkable ring signatures with an anonymous broadcast protocol to have people participate and like generate inclusion lists without like being linked to a specific set of transactions. So yeah, this is how I see the potential like future of censorship resistance, or what it could look like on Ethereum. Right now it's more like of a vision, and I would love like for anyone that's interested in contributing to that vision to join and reach out. But yeah, I think it's very exciting, and you have like a bunch of different research directions you can go into. Thanks.
Hi, thank you very much for the presentation. I just wanted to make clear one thing. Can you help me understand the inclusion pipeline of transactions into the block? What are the incentives for the participants in the committee and the builders to include a particular transaction? Is the design objective here just to restrict the censorship altogether, or is it to have a more uniform inclusion of all transactions in the blocks? So in other words, why would a committee member include a potential transaction into the list, versus why would a particular builder select one particular list into his block?
Yeah, okay, so that's a good question. IL committee members in the current version of Fossil don't have a specific reward mechanism, so we just rely on altruistic behavior. We think honest ones will just monitor the mempool, public mempool include transactions according to a rule. It can be like, I don't know, based on the amount of time a transaction was pending in the mempool, for example, or based on priority fees, or a combination of both. So that's how like IL committee members include transactions in their list. And the builder is like, well, he will try to probably make profits. Let's say he doesn't want to censor a particular transaction, then he will just probably include like the ones that are paying him the most and like do his whole MEV thing. But the condition for its block to be valid is going to be to have all the transactions in all the ILs included in its block. So it's basically he does what he wants as long as the transactions in the ILs are included in its block. So it's more of like a constraint. So yeah, that's and his incentives are probably driven by profit. If he wanted to exclude a transaction, it has like different ways of doing it. So he can just like miss its block and be like, okay, like I don't want to include that transaction, so I'll just not propose a block at all. He can also like try to stuff its block, but it's very expensive to do this. But otherwise, he has to include it for its block to be valid. It's like a hard constraint, and it's part of the fork choice. And otherwise, yeah, the block won't be canonical.
Thank you. And in future versions, you could think of more sophisticated reward mechanisms.
Exactly. That was like the incentives part of thing. Like, how do you want to design a mechanism that, for example, rewards IL proposers based on their contribution? Imagine you want to, for example, reward IL committee members that are including transactions that no one else wants to include. So you have, let's say, an inclusion fee, and it's distributed across the number of people that included that specific transaction. So if you aren't the only one, you'll collect all the fee. But if you are like 10, then it will be split into 10. So this incentivizes like people to actually include transactions that might not be included by others. That's one way we could design it. But I think it's like a very exciting kind of research direction to explore. I don't think we have like a consensus or like a really definite way of doing things. It's, so yeah, if anyone is interested.
Thank you.
Yes.
So I had a question about includer separation.
Yeah.
You mentioned different rewards that participants can get, like basically different levels of includers and rewards they can get. I was wondering if there are any designs on punishment, like on bad, undesirable behavior by different includers and how you account for that.
Yes, that's a good question. I think the very bad punishments should be for execution proposals. Those are like the ones that are supposed to be sophisticated, and if they are separated from consensus duty, you can actually punish them. For IL committee members, they're not, like if we want them to be like quite decentralized, not very sophisticated, then we probably don't want to punish them too much in case they make a mistake or like they don't see all transactions or like they're offline for some reason. So I wouldn't like go for like punishments, but like, I mean, the punishment in itself would be to miss the rewards. I probably wouldn't like design an actual penalty for them, because if we want them to be like super decentralized and like kind of participate with minimal requirements, we don't want to make it too hard on people that want to participate, but for some reason got offline because, I don't know, their internet connection was cut off or whatever.
Gotcha. Thank you.
Thanks.
Let's thank the speaker again. And then for the last speaker of the session, we have Pranav Dalamidi from A16Z, who will be discussing Fossil and Braid all together.
Yeah. Hi, I'm Pranav. So it's going to be kind of discussing Fossil and Braid and trying to put them into context. There's a lot of kind of moving parts going on, so hopefully this will be helpful. All right. Start off with just disclosures. Opinions are my own, et cetera, standard stuff. Okay, so kind of from the two talks before, we've kind of seen there's two main problems that I think both of these solutions are trying to address. And the first one is this idea of short-term censorship, right? So we'll kind of get into a more detailed definition of this later. But you can kind of think of this as basically the ability of any adversary to prevent some target transaction from landing on the chain. And in particular, we're going to focus on the fact that this censoring can happen over the course of a single slot. You can imagine kind of wanting censorship over multiple time slots, right, for just maybe like making sure a peer-to-peer payment isn't censored, maybe you're fine if this takes like 2 blocks, for example. But for the purpose of this talk, we'll kind of really focus on this notion of short-term censorship. And this is kind of what Milesh was more talking about that's very relevant for things like running auctions, participating in DeFi, for liquidations, all this type of stuff. The second thing is this notion of last mover advantage. And this is basically just the advantage some party has in being able to influence kind of the block production pipeline later than everybody else can, right? So in Ethereum today, kind of the proposer knows they will always move last, right? And if they were self-building their block, they can kind of have an enshrined power to include transactions which could be trades that reflect a fresher state of prices than kind of anybody else can. And so we'll kind of talk about how Fossil and Braid kind of address these 2 main issues. And so talk about kind of why you might care about these issues. Kind of Milesh laid out some examples of how if these issues aren't addressed, kind of various DeFi applications can be broken. And there's some clear kind of examples we all know of how censorship can be really harmful to kind of the purpose of what blockchains are supposed to do. And I think there's kind of 2 main distinctions that can be drawn. And the first one is kind of Ethereum's kind of focus more as a settlement layer, right? And so this is really kind of high-value transactions, but not necessarily execution-wise, just maybe thinking of Ethereum more as a very secure bank, where it's kind of like the place where all these proofs for different L2s are stored, it's where all the DA is stored. You just want this thing to be very safe and to kind of do kind of large value transfers, but not necessarily kind of be very highly performant or kind of be the place where markets are discovering prices in real time. And so kind of for this version of Ethereum, short-term censorship resistance is still quite important. Kind of the very strong version I'm mentioning, where you really want it to have strong guarantees on the course of a slot, might not be quite as important. For this version of the world, maybe you're fine if your bank transfer can't be censored over the course of 30 seconds instead of just kind of the one block 12 seconds we have today. I think the second road that you could see Ethereum going down is like actually trying to reach this vision of being a place where real-time DeFi happens, where there is price discovery happening on chain, kind of where the largest markets really do have a significant presence on Ethereum, and where people are kind of day-to-day trading. They go to Ethereum as an option for that. And so here, the L1 probably has to be kind of have much higher execution than it has today, kind of have lower latency. And here, the short-term censorship resistance kind of we're talking about, and the strong version of it is quite important, kind of for all the reasons Milesh was talking about, of how without it, all these kind of on-chain auctions and stuff kind of fall apart. And additionally, this last mover advantage is also a big problem now, kind of for the same reasons that Milesh kind of brought up in his examples. If you're running these kind of on-chain markets, and there's always some trader who has this enshrined power to move after you, it's going to kind of make all of these markets break. And so if kind of Ethereum wants to go down this road of really supporting these use cases, then solving both of these issues, I think really is a first-order concern. So now let's get into some kind of more technical details of what I'm talking about here. And so we'll say that for short-term censorship resistance, we kind of want some way to compare Fossil and Braid, right? Kind of, these are very different mechanisms. There's different types of players. It's hard to say kind of what does it even mean for one to be more censorship resistant than the other. And so here's a very loose definition that's not kind of formally mathematically defined, which is still kind of a work in progress. But I think it gets the spirit across, where basically we'll say protocol A is more short-term censorship resistant than protocol B if kind of holding all else equal. If I pick a single transaction T, and an adversary's only goal is to prevent this single transaction T from landing on chain, then the minimum payments this adversary has to make to some participants in this block production game are higher under A than they would be under B. And so kind of in particular, there's this annoying thing with censorship resistance where, if a block is already full of transactions and your transaction wouldn't have gotten in anyways because it was too low value, does that mean it's censored? Not really. And so kind of with this definition, the adversary has to pay 0 in both cases. But if this was really like a high-value transaction that should have landed on chain and was paying a high enough fee, then the kind of relative amount an adversary have to pay either the inclusion list committee members or maybe the proposer, you want to kind of see what that ratio looks like. Okay, now going for last mover advantage, this one is even less well defined. I think it's kind of tricky to talk about what it actually means for somebody to act on the latest information and kind of what it means to kind of affect the block production process. But here, it really is just referring to this idea that, or the intuition behind it is that, at least in Ethereum today, there is a single proposer that really does know for sure that they are ending the block production game, right? They are always the last one to kind of sign a block and then kind of have that announced to the world. This is a bit more complicated with the fact that relays exist in practice. So really, relays are the ones who move last in the current state of Ethereum. But we'll kind of ignore some of those distinctions today and assume, for the sake of just simplicity, that proposers are self-building. And in this case, we really see a distinction between MCP and kind of the version of Fossil or Ethereum, where in MCP, at least there are multiple different parties where nobody has an enshrined kind of power to end the block production game, right? All these proposers are kind of simultaneously competing with each other. And any one of them doesn't know if kind of, if they are the last one to move, they might have a very short time span in which to take advantage of. And so now we'll kind of get into the kind of two main solutions that were kind of just discussed by Tomas and Milesh. So the first one, I'm going to call kind of this setting of constrained single proposer mechanisms. And kind of the idea being here that we take what we already have today with this traditional single proposer protocols, and we just add this notion of additional committee. And this committee is basically responsible for like adding some constraints on the proposer, right? So in Fossil, this is an inclusion committee. They're responsible for announcing transactions that the proposer is kind of forced to follow. The second category is what I'm calling multi-proposer protocols, of which MCP is kind of one example. And the distinction here is that in multi-proposer protocols, you explicitly take the power that the proposer has and kind of split this up amongst multiple parties. Right, so there's kind of multiple equally powerful parties who are responsible for proposing subblocks, and there's no kind of single canonical party that has this power of like kind of deciding the state transition. Okay. So now let's get a bit more into kind of technically what I mean when I say these different kind of settings. Right, so yeah, constrained single proposer protocols, there's a committee that acts before the proposer, with the inclusion list being kind of the main example, but even here there's kind of two main distinctions, right? So Fossil uses this notion of a conditional inclusion list. There's also notions of an unconditional inclusion list, with kind of the distinction being that in an unconditional inclusion list, kind of the transactions the inclusion committee proposes are kind of required to be included by the proposer no matter what. Whereas in the conditional inclusion list, the proposer only has to include them as long as there's kind of empty space in their block, right? So a proposer can't make, a block with 20 million gas and have 10 million empty gas, and then just kind of have these inclusion lists kind of floating around that have these transactions they didn't include. Now, in theory, you got to kind of think of different things too, right? So I don't think this would be a good idea for Ethereum, definitely. But you can imagine things like if the committee hears some price movement, they're forced to include certain liquidations, right? So I think Fossil is one example of what kind of makes the most sense for Ethereum. You can imagine in general for other blockchains potentially kind of a very broad range of what these committees end up doing. And then kind of one of the last kind of choices you can make is the notion of a TFM, right? So TFMs are transaction mechanisms which traditionally kind of govern how much user transactions pay and how much the block producer is kind of paid and how much is burnt and whatnot. And now, since we're adding all these additional agents into the game, kind of with the inclusion committee, you can imagine that members of this committee are paid some amount. Maybe a user pays a different amount to get their transaction included in an inclusion list via being fully included in the block. Maybe they pay more, maybe less. There's lots of different kind of design choices you can make here. Fossil kind of makes the opinionated choice to not have a TFM that affects the inclusion list at all, and kind of just have the same 1559 inclusion, same 1559 TFM we have today, with just kind of this added functionality that the inclusion list constrains the proposer more. But you could imagine these more general choices. So now just to kind of recap the actual choices Fossil makes out of this design space, right? So as we discussed, it's conditional inclusion lists. There is no explicit intended allocation rule for the inclusion committee members, right? So the point of this basically is that to incentivize kind of the decentralization of the inclusion committee, We don't want something that's like only include the highest fee, priority fee transactions in the list, right? We might want some other rules like include transactions that have been in the mempool for a while that haven't been picked up yet. And the idea here is basically deprioritizing some of the like very high value MEV transactions and prioritizing some things more like peer-to-peer payments or something, so some other applications where for some reason the decentralized block producers aren't including them. So Fossil, as I was just mentioning, there are no economic incentives for any of the inclusion committee members, kind of for similar reasons. The idea being that hopefully by not having any kind of explicit economic guarantees to or explicit economic payments, these committee members, they might instead kind of just behave honestly and not pay too much attention, and maybe they just run this software on their node and hopefully just pick up stuff without caring too much about the payments. But this is an explicit choice that does have some other kind of consequences in terms of what you can say about the security of the protocol. And so for the purposes of kind of our analysis and talking about kind of what we can say about these two different regimes, I'm going to assume the members are just non-strategic because of this, and they are following an inclusion rule of actually including the highest priority fees, right? So that's not what it is in practice. But just for the sake of tractability and kind of getting some type of formal analysis, I'll assume that. And so kind of these two main choices of like not having explicit inclusion rules and not having these incentives are really to like not favor these high value transactions and instead kind of support the central persistence of kind of the more lower value transactions that might just be floating around. Okay, so now let's get into the analysis of Fossil, kind of on these two main problems that we mentioned. And so in order for an adversary to censor a target transaction, they either have to fill the entire inclusion list of kind of all the committee members, or they have to fill the block, right? It's because we're using a conditional inclusion list. If an adversary kind of bribes the block producer not to include a target transaction, and then also fills the entire block, then then you're totally fine, right? If the block is full, the inclusion list can be ignored. And importantly here, I'm only talking about over the course of one slot, right? So naturally, this gets extremely expensive if you're filling multiple blocks over time, since the gas price would kind of increase accordingly. Over a single block, it's still expensive, but you don't have these dynamics of kind of exponentially increasing gas prices. It would just be kind of, filling the block requires just paying the base fee of all the unfilled space, right? So if the block is already 25 million gas for some reason, you just have to pay 5 million gas worth of the base fee and kind of the tip of this target transaction to censor it. And now, kind of with the assumption I made of the inclusion committee members are following this rule of including the highest priority fee transactions in their lists, now you could also, as like a separate attack vector, basically just if the target transaction has a relatively low priority fee, maybe towards the tail end of kind of the inclusion list, you could also just outbid that explicit priority fee and send it to all the inclusion list members, and maybe they would include it, right? And so this is how this would work in practice. Again, is tricky if there's even one person who's just honest and ignoring incentives, and is just kind of willing to like include your transaction regardless of what you bribed them, then like this isn't an attack vector anymore. But kind of for the formal purposes of saying kind of can we quantify what the cost of censorship is, kind of with this analysis, it ends up being the minimum of the cost to fill the inclusion list and the cost to fill the block, right? Kind of either or with conditional inclusion lists, will let an adversary censor the target transaction. Okay, now let's talk about last mover advantage. So Fossil really does not address last mover advantages, right? It kind of takes the very traditional Ethereum supply chain we have now, right? With the proposer kind of moving towards the end of their slot. And that's all kind of the same, right? So as Lush was mentioning, kind of if you have these like very time-sensitive transactions, they're coming in towards the end of a slot. The proposer still does have the ability to move kind of after everybody else. And really Fossil just doesn't, it's not claiming to address this, and it really can't in some way. And so this isn't kind of a formal statement, but really this is just a problem any kind of constrained single proposer protocol will have, and that the constraints have to be announced ahead of time for the proposer to kind of follow the constraints. And so if new information arrives in that kind of delta, there's no way for the committee to like know about information to kind of enforce that on the proposer. And so really, I think any kind of protocol in this kind of design space is going to really struggle to address the last mover advantage in particular. Okay, now let's talk about kind of the space of multi-proposer protocols. And so kind of the defining characteristic is that instead of a single proposer per slot, there's explicitly multiple proposers with equal power in a given slot. Right? Now, each proposer will propose a sub-block of transactions, right? So similar to a block today. And then basically now the protocol has this extra rule it doesn't have today, that has to somehow aggregate these proposals into a canonical block. And then this thing decides exactly what's confirmed and kind of in what order and kind of does all the transfers. You imagine lots of different aggregation rules and different TFMs that kind of do this, right? You can maybe every sub-block is like 2K gas worth of transactions, and you have like 5 proposers, and maybe the overall chain can accept a block of like 5K gas, right? And so you somehow aggregate things and like filter like the top half. Maybe you take the entire union of everything. Maybe there's some other clever thing or some other thing that depends on the app layer semantics. There's really lots of different choices you can make in the aggregation level. And then the TFM part, it's not clear how do you pay the different proposers based on what transactions actually get included. How do users pay? Now you can have a richer design space. Maybe users pay more if they're included in multiple sub-blocks, even if they're only confirmed once. Maybe people pay if they're in sub-blocks but not fully confirmed, right? Like there's a lot of different TFMs that you could use that are much richer than kind of what we have in the standard single proposer setting. And yeah, so this is really a very broad design space. So now kind of just narrowing in on Braid and kind of what Melissa was talking about and kind of the exact, or one set of choices you could make. Again, kind of for the trying to get towards a more formal analysis of what properties we have here. And so one important thing that will be important in the last look part is this idea of simultaneous release, right? So Malesh mentioned the weak notion and the strong notion. And so really here we're talking about the strong notion for like the no last mover advantage. And basically you can imagine that you have various cryptographic techniques, right? So delay encryption was proposed. You also have some notion of threshold encryption. Just various kind of forms of encryption. So even if people are submitting their blocks at kind of slightly different intervals, still overall nobody can see somebody else's block and nobody is kind of waiting to see somebody else's block before they move, right? So in the case where you just submit blocks in plain text, then timing games are very bad. If nobody, like really nobody wants to be the first to move, everybody wants to be the last to move. At least with the property of people can see each other's block contents. Even though there are gains to waiting later, they're not quite as stark. So the effects of timing games might not be quite as bad with these kind of cryptographic techniques, but these are still kind of very much work in progress. The aggregation they use is kind of just take the union of all the subblocks, right? So if any transaction is at least in one subblock, the idea is it should be confirmed. The ordering rule is also TBD and very important in terms of like how it'll actually function in practice. This doesn't turn out to be important for our analysis for the two kind of properties we talked about, so I'm not going to address it for now. And then the fee mechanism, this notion of conditional tipping, Malesh mentioned of this idea that you have this little t and this big T, and if only one person includes a transaction, they get the big T, and if kind of multiple people include it, they each get the little t. And so this is what we'll use to kind of talk about the short-term censorship resistance of the protocol. And then the exact consensus is also kind of up in the air, right? For Fossil, it's kind of more specified, kind of as Tomas was mentioning, how the flow would work. For Braid, it's still a work in progress of exactly how you'd implement some of these properties sort of consensus. But again, not immediately relevant to our analysis, so we're not going to address it too much. OK, so let's get into kind of the analysis. Again, on these two properties we want. Right, so for short-term censorship resistance, the nice thing is basically with this conditional tipping mechanism, you get at the very least this linear increase in the cost of censorship with the number of proposers, right? It's at least you're paying like k times little t, whereas before you might have just paid this t. And with the conditional tipping, you can really make this much larger. In some model, you could say that it's unbounded by making t kind of as large as you want. I think that that's dangerous, right? Like the larger the big T gets in the conditional tipping mechanism, the more incentives there are for kind of the proposers to collude and like kind of split that big T amongst themselves, right? And so particular, like as soon as big T gets bigger than k times little t, now there is kind of an equilibrium where everybody's colluding and they're all getting more value than they would have if they just kind of all included the transaction. So I think it's still unclear exactly how big you can make this big T while it's still kind of having the protocol be secure. But in any case, you still get at least this linear increase in terms of what we had before. And this just comes from this game theory of proposers are competing with each other, and the fact that if somebody doesn't include a transaction, if nobody includes a transaction, one person can make the small deviation for a large gain for themselves. So this is kind of really explicitly using the multi-proposer part of this to get the short-term censorship resistance. Okay, so now talking about last mover advantage. So this is really where MCP kind of differentiates itself from Fossil and kind of adds some new properties. And so the really important thing is, like, once you have simultaneous release, no proposer has certainty about the included transactions and, importantly, the state transition until after the slot ends, right? So if there's 5 people and I'm one of the proposers and I don't see any of the other people's blocks, I really don't know what will actually happen on chain until after the slot ends. And so this kind of addresses some of the really bad forms of the last mover advantage, right? So in particular, when one party can see, even if you have these like encryption kind of protocols, kind of as much as mentioning, even one person being able to act later can kind of really hurt things. But here, at least, nobody seeing what everybody else does makes the equilibria a lot nicer in terms of what happens kind of on chain. And yeah, it's especially this point that there's no proposer that has like an enshrined advantage, right? So there still might end up being some form of last mover advantage, right? If somebody has a 20 millisecond shorter latency, maybe they do end up kind of getting included later. Maybe they do end up proposing a bit later. But at least this is now a competitive process, right? It's not kind of like every slot we are rewarding one person with the right to propose as late as they possibly can, and they have no competitive pressures to kind of announce earlier. At least now there are these equal parties, and we can kind of think about mechanisms where we incentivize them to propose as close to each other as possible. So in this competition, the hope is, even though these proposers might still have, they definitely still have advantages compared to non-proposers, right? So if I'm not a proposer in a slot, I still have to send my transaction to somebody who then includes it, and so there's some inherent latency delay there that a proposer wouldn't have. But the hope is, like, even this competition amongst the proposers is enough to keep these on-chain markets competitive, even if it's tricky to get like actual users the same kind of market advantage that the proposers have. Okay, so kind of wrapping up and trying to put these kind of the main takeaways. So both the constrained single proposer, in particular Fossil, and multi-proposer architectures, they definitely can offer short-term censorship resistance guarantees with the right TFM. Right, so you can imagine adding more bells and whistles in terms of paying the inclusion committee more, and now you could actually get really strong guarantees with Fossil, kind of along the lines of the braid kind of analysis with conditional tipping and stuff like this. But to some extent, Fossil makes the opinionated choice to not do this, kind of at the favor of lower value transactions. This is kind of the idea that Tomas was talking about a bit, of trying to incentivize kind of this decentralization of the inclusion committee members, and that the second you start offering kind of explicit economic incentives, then it's probably the case that people who are better at being inclusion committee members will get paid more than people who are worse. And that naturally opens up these outsourcing type things of people, delegating their stake to other people that would be really good at kind of offering these guarantees and, offering things like pre-confirmations and whatnot. And so Fossil, basically, to try to prevent this happening, makes a choice to like not even have these incentives. And the hope that no IL boost type solution pops up. And then, the kind of the last thing is that if Ethereum really is focused on going with kind of this more real-time DeFi kind of application, there is no clear way to address the last mover advantage in Fossil, and you really do need at least some type of MCP. In particular, Braid is focused on trying to kind of address some of these problems. And I'll just close out with kind of the open problems that kind of I think both of these different solutions have. So with Fossil, I think the main one that I see is kind of what I've been discussing of what is the right economic model in terms of should inclusion committee members be paid, and then in particular kind of this ties into like how do you expect the IL to be part of the transaction supply chain. I'm personally a bit skeptical of kind of relying on like a solo staker type class of people to be kind of responsible for like kind of holding up the strong guarantees you might want. In particular, kind of looking down the road 5, 10 years, kind of what does that fraction of the overall stake look like? And even though you have like conditional versus unconditional inclusion lists, I think actually these things look, the only case where a conditional list is different from an unconditional list is where the block is already full, which by design is not many Ethereum blocks. And so kind of, if the block is in full, conditional inclusion lists also offer pretty strong inclusion guarantees people might want to sell. And so I could definitely see a world where even though Fossil doesn't make any incentives to the inclusion committee members, you end up still having some type of IL boost. And so you might still want some kind of explicit economic mechanism in the front to kind of at least reason about what this might look like and try to drive the incentives in the right way than just kind of fully letting the market decide how to best use this stuff. And now on Braid, I think the main thing for practice is this notion of an ordering rule, right? So nice thing with Fossil is you don't need an ordering rule. With Braid, you really do need to choose at least some ordering rule, right? Whether it's by decreasing priority fee or something more fancy, any rule you choose has large implications on kind of how the chain functions. I personally still think it's an open question of like if these deterministic ordering rules are like strictly better than having explicit block building, right? There's different incentives in like how you bid for gas that can have negative externalities and just by ordering by priority fee that are kind of not quite there in the explicit block building case, and right? The explicit block building case has its own kind of downsides with things like sandwiching and other kind of negative externalities. But I still think it's an open kind of problem under like which of these regimes do you really want to be in. Braid forces you to be in one of them in a deterministic sense, since the protocol has to aggregate things in some canonical way. But it's unclear to me if that's a downside or an upside quite yet. And then the other main thing is kind of how do we get this cryptographic solution for spontaneous release. So I kind of hand-waved some different solutions. To really get this in production, they shouldn't be hand-wavy. They should be like kind of very well specified, and we should really understand the kind of technical limitations there. I think that's still kind of a very work in progress. Kind of the last thing is understanding what the builder market looks like in an MCP rule is also very unclear, right? In the Fossil rule, it feels, at least in terms of the proposer, the like traditional PBS stuff, you know, it's probably just that the inclusion committee makes some constraints and then the builder hears about them and follows these constraints. And so things should generally kind of follow as they do today with maybe a couple exceptions. But with Braid, this is very different, right? Like now, the fact that nobody knows what the state transition will be, kind of by design, builders can't offer guarantees like revert protection, stuff like this, right? And so it's unclear exactly, is there still like a MEV boost thing where some subset of proposers end up, you know, having some builder build their blocks? Do you see like kind of collusion and cartels of the kind of groups of these proposers effectively acting as a kind of a larger block builder? I'd say it's still very early days understanding kind of what properties do you need on this the mechanism ends up happening in order to like still retain the good properties that we have in the kind of more traditional analysis if proposers are all self-building. So yeah, that's all I have, so thanks.
So unfortunately, we don't have time for questions, so please find Pranav during the break. This concludes the block code construction session, and we'll reconvene in 10 minutes. That's